Hello and welcome to my video on generator control. This is part one of a two-part series. We're talking about how and why we have to control the electrical generator of airplanes. These principles apply everything from the smallest airplane like a little Cessna 140 all the way up to what we use, large modern transport category airplanes. In this example though, we're just going to focus on typical generator control of small airplanes like a Cessna 150 or 172, something like that. So let's get to it. What we've got here first is just a little basic drawing here, real simplified, of our generator circuit, where I have an armature that rotates, and then our fixed field coil, and then of course our aircraft load. And the aircraft load is anything electrical on the airplane: lights, pitot heat, radios, popcorn maker, etc., etc. You'll see that all three of these are in parallel. So recall from our basic DC that the voltage on the armature, or across the armature, will equal the voltage across the field, and that will equal the voltage across the load. And then recall that the total current is field current plus load current. And one more thing to recall: the magnetism of the field is directly proportional to the voltage in the armature. As the field coil magnetism here increases, the voltage in the armature will increase. So let's look at a typical case that we have going on. So we spin up our generator without any control, and the armature voltage will begin to increase as the armature is spinning faster and faster. As that increases, of course, the voltage on the coil increases, the voltage on the load increases. All so far so good. Let's take a look. As the voltage on the coil increases, what we said here, the current through the coil will also increase, and that makes our magnetism of the field increase, and that will cause the voltage on our armature to continue to increase. This will come right back around, and we go through the same thing again and again and again. And without any control, the voltage of the armature will just plain get too high. So that is the problem. What are we going to do about it? Well, pretty simple solution. We're going to control the current through the field coil. So here's a little example of a voltage regulator. We show it as a changing resistance here. And it's not actually, but it sort of is. Don't worry about that. And again, now remember, the resistance of the field equals the resistance of the voltage regulator resistor, and the resistance of the field coil. So in this case, when my voltage on the armature goes up, I adjust the resistance of the voltage regulator to increase. If that increases, the current through the field will decrease. The magnetism of the field will decrease. If the magnetism of the field decreases, the voltage in the armature decreases. So what happens is we're constantly adjusting the resistance of the field, and the armature voltage is going up and then down and then up and then down, back and forth, back and forth. In a well-designed regulator, if this happens fast enough, although our voltage will be doing a little of this, it's so small it's not doesn't cause us any problem. Let's look at this solution a little better. Rather than have a variable resistor, let's do something else for us. Here we have switch VR right there. Let's erase this switch thing here real quick. Oops. Fix this, pardon me. So there's switch VR, like we said. And this is the voltage regulator switch, and when switch VR is closed, the resistance of the field equals the resistance of the coil. This switch is closed, current is going to flow right through here, not through the resistor at all, no big deal. When SVR is open, if we have this path open, current has to flow. Keep breaking my circuit here. Current has to flow through the resistor and then down through the coil. So when SVR is open, resistance of the field equals resistance of the coil plus resistance of the voltage regulator. Pretty simple. SVR closed, we've seen already that our armature voltage will increase. We then open the switch, the resistance of the field will increase, and when the resistance of the field increases, the current of the field will decrease, and when the current of the field decreases, the magnetism decreases, of course, and then the voltage in the armature decreases. And here's just a little diagram of a little better of how it actually works. Remember again, we end up the armature, field, C1, and load. C1 is this coil right here. We actually have two coils on this relay, C1 and C2. C1 you see is in parallel to the armature, and C2 is in series with the field. That's really what happens. When the voltage on the armature increases, the voltage here on C1 will decrease, the relay energizes, this resistance goes up, current goes down, the magnetic field goes down, the voltage of the armature goes down. The whole purpose of this field being in series is to help the magnetic field collapse quicker so that we get a faster voltage regulation, so there's not as much lag. So I hope that helped give you some basic principles of a voltage regulator, and thanks for viewing this video.